Welcome to Class 11 Mathematics. Today we begin with Chapter 1, Sets. This fundamental concept was developed by the German mathematician Georg Cantor in the late 19th century, and today it forms the foundation of almost every branch of mathematics. So what exactly is a set? A set is a well-defined collection of objects. These objects could be numbers, people, letters, or anything you can think of. The key requirement is that you must be able to clearly decide whether any given object belongs to the collection or not. For example, the vowels in the English alphabet form a set, A, E, I, O, U. The objects in a set are called elements or members. We use the Greek symbol epsilon to denote membership. If an element A belongs to set A, we write A belongs to A. If B is not in A, we write B does not belong to A. This notation is essential for working with sets. There are two main ways to represent a set. First is the roster or tabular form, where we list all elements within curly braces. For example, the set of even numbers less than 7 is written as 2, 4, 6. Remember, the order doesn't matter, and we don't repeat elements. The second method is set builder form. Here, we describe elements by a common property they all share. We write it as the set of all x such that x satisfies some property. For instance, the set of vowels can be written as v equals x such that x is a vowel in the English alphabet. Now, let's talk about a special type of set, the empty set. Also called the null set or void set, it contains no elements at all. We denote it by the Greek letter phi or empty braces. An example would be the set of natural numbers between 1 and 2, which doesn't exist. Sets can be finite or infinite. A finite set has a definite, countable number of elements. An infinite set goes on forever. The set of natural numbers 1, 2, 3, and so on is infinite. We use n of s to denote the number of elements in a set S. Two sets are said to be equal if they contain exactly the same elements. The order in which elements are listed doesn't matter. Also, repeating an element doesn't change the set, so the set 1, 2, 3 is equal to the set 3, 2, 1, and also equal to 1, 1, 2, 3. A very important concept is that of subsets. Set A is a subset of set B if every element of A is also an element of B. We write this as A is a subset of B. Every set is a subset of itself, and the empty set is a subset of every set. Let's learn some important standard number sets. N represents natural numbers, 1, 2, 3, and so on. Z represents integers, including negative numbers. Q represents rational numbers, and R represents real numbers. These sets are nested. Natural numbers are a subset of integers, which are a subset of rational numbers, which are a subset of real numbers. Intervals are special subsets of real numbers. An open interval, written with parentheses as AB, contains all numbers between A and B, but not A and B themselves. A closed interval, written with square brackets as AB, includes both endpoints. The length of any interval is simply B minus A. In any particular context, there's usually a main set that we're working with. This is called the universal set, denoted by U. All other sets we discuss are subsets of this universal set. For example, if we're studying integers, the universal set could be the set of rational numbers or even real numbers. Venn diagrams are a wonderful visual tool for understanding sets. Named after the English logician John Venn, these diagrams use a rectangle to represent the universal set and circles inside to represent subsets. The elements are written inside their respective circles, making relationships easy to see. Now we come to operations on sets. The union of sets A and B, written as A union B, contains all elements that are in A or in B or in both. Common elements are taken only once. This operation follows the commutative law. A union B equals B union A. The intersection of sets A and B, written as A intersection B, contains only the elements that are common to both A and B. If two sets have no common elements, their intersection is empty, and we call them disjoint sets. Like union, intersection is also commutative. The difference of sets A and B, written as A minus B, contains elements that are in A but not in B. Unlike union and intersection, order matters here. A minus B is not the same as B minus A. Interestingly, the three sets A minus B, A intersection B, and B minus A are all mutually disjoint. The complement of a set A, denoted A prime, is the set of all elements in the universal set U that are not in A. In other words, A prime equals U minus A. An interesting property is that the complement of A gives back A itself. This is called double complementation. De Morgan's laws are fundamental relationships in set theory. The first law states that the complement of A union B equals A prime intersection B prime. The second law states that the complement of A intersection B equals A prime union B prime. In simple terms, the complement of a union is the intersection of complements, and vice versa. Let's review the key properties of complements. First, A union A prime equals the universal set U. Second, A intersection A prime equals the empty set. Third, the complement of the empty set is U, and the complement of U is the empty set. All these can be beautifully verified using Venn diagrams. The distributive laws connect union and intersection operations. The first states that A intersection with B union C equals A intersection B union A intersection C. The second states that A union with B intersection C equals A union B intersection A union C. These laws are essential for simplifying complex set expressions. Sets have many practical applications in real life. In probability theory, sets help us calculate chances of events. In databases, set operations help filter and query data efficiently. Classification systems in science use sets to categorize objects. Even in computer science, many data structures are built on set concepts. When solving problems with sets, always start by drawing Venn diagrams to visualize the situation. Apply De Morgan's laws to simplify complex expressions. For counting elements, use the formula n of A union B equals n of A plus n of B minus n of A intersection B. Break complex problems into smaller, manageable parts. Here are some key formulas to memorize. For counting, n of A union B equals n of A plus n of B minus n of A intersection B. There's also a formula for three sets. Remember that A minus B equals A intersection B prime, and a set with n elements has exactly 2 to the power n subsets. Watch out for some common mistakes. Don't confuse the belongs to symbol with the subset of symbol. Remember that in set difference, order matters. Don't forget to consider empty set cases in your solutions, and be careful when applying De Morgan's laws. The union becomes intersection and vice versa. Let's summarize what we learned in this chapter. Sets are well-defined collections of objects. We studied operations like union, intersection, difference, and complement. Venn diagrams help us visualize relationships between sets. De Morgan's laws connect these operations beautifully. This chapter forms the foundation for understanding relations and functions, which we'll study next. Thank you for joining Chapter 1 on sets. Welcome to Chapter 2, Relations and Functions. In this chapter, we'll learn how to connect pairs of objects from two sets, understand the concept of relations, and then explore functions, one of the most important concepts in mathematics. This work was pioneered by G.W. Leibniz in the 17th century. Let's start with ordered pairs. An ordered pair is simply two elements written in a specific order, like AB. The key point is that order matters. The pair AB is different from BA unless A equals B. Two ordered pairs are equal only when their corresponding elements are equal. The Cartesian product of two sets A and B, written as A cross B, is the set of all ordered pairs where the first element comes from A and the second from B. If set A has P elements and set B has Q elements, then A cross B will have P times Q elements. Note that A cross the empty set gives the empty set. Important properties of Cartesian products. First, A cross B is not equal to B cross A. The operation is not commutative. Second, A cross A gives ordered triplets of the form A, B, C. R cross R represents all points in a two-dimensional plane, while R cross R represents three-dimensional space. Let's see an example. If A equals 1, 2, and B equals 3, 4, then A cross B gives us four ordered pairs, 1, 3, 1, 4, 2, 3, and 2, 4. But B cross A gives 3, 1, 3, 2, 4, 1, and 4, 2. These are different sets, showing that order in Cartesian products really matters. Now let's understand what a relation is. A relation R from set A to set B is simply a subset of the Cartesian product A cross B. It describes a connection or relationship between elements. We can write it as R equals the set of ordered pairs x, y, where x is in A, y is in B, and x is related to y in some specific way. Every relation has three important components. The domain is the set of all first elements in the ordered pairs of the relation. The range is the set of all second elements. The codomain is the entire set B. Remember, the range is always a subset of the codomain. How many relations can exist between two sets? The total number of relations from A to B equals the number of possible subsets of A cross B. If A has P elements and B has Q elements, then A cross B has P times Q elements. The number of subsets, and hence relations, is 2 raised to the power PQ. Arrow diagrams are a great way to visualize relations. Draw 2 sets and use arrows to show which elements are related. The arrows point from elements in the domain to their images in the range. This makes it easy to identify the domain and range at a glance. Relations can be classified into different types. An empty relation has no elements related. A universal relation relates all elements. A reflexive relation has every element related to itself. We also have symmetric and transitive relations. We'll explore these properties in more detail in later chapters. Now we come to functions, a special and very important type of relation. A function from set A to set B is a relation where every element in A has exactly one image in B. No element can have 2 different images, and every element must have an image. We write this as f from A to B. Let's understand function notation. When we write f from A to B, it means f is a function with domain A and codomain B. If f of A equals B, we say B is the image of A, and A is the preimage of B. The set of all images forms the range, which is always a subset of the codomain. Real-valued functions are those whose range is either R or a subset of R. A real function has both its domain and range as subsets of real numbers. Most functions we study in school mathematics are real-valued functions. Their graphs can be drawn on a coordinate plane. The identity function is the simplest function, f of x equals x. Every element maps to itself. Both domain and range are all real numbers R. When you graph it, you get a straight line passing through the origin at a 45-degree angle to both axes. A constant function always gives the same output regardless of input. If f of x equals c, where c is some constant, then every input gives output c. The domain is all real numbers, but the range is just the single value c. The graph is a horizontal line at height c. Polynomial functions are functions like f of x equals a0 plus a1 times x plus a2 times x squared, and so on, up to n times x to the power n. Here n must be a non-negative integer. Examples include f of x equals x squared minus x plus 2, or g of x equals x cubed. All polynomial functions have domain equal to all real numbers. Rational functions are ratios of 2 polynomials, f of x equals p of x divided by q of x. The key thing to remember is that the domain excludes any value where the denominator q of x equals 0. For example, f of x equals 1 over x has domain all real numbers except 0. The graph often has vertical asymptotes. The modulus function, also called absolute value, is written f of x equals the absolute value of x. For non-negative x, it equals x. For negative x, it equals negative x. The domain is all real numbers, and the range is all non-negative real numbers. The graph is V-shaped and symmetric about the y-axis. The signum function tells you the sign of a number. It returns 1 if x is positive, 0 if x is 0, and negative 1 if x is negative. The domain is all real numbers, but the range is just 3 values, negative 1, 0, and 1. It's useful for determining the sign of any real number. The greatest integer function, also called the floor function, is written f of x equals square brackets around x. It returns the greatest integer less than or equal to x. For example, the greatest integer less than 3.7 is 3. For negative 2.3, it's negative 3. The graph looks like a series of steps. Now let's learn about the algebra of functions. We can add 2 functions, f plus g of x equals f of x plus g of x. Both functions must have the same domain, or at least overlapping domains. The domain of the sum is the intersection of the individual domains. For example, if f of x equals x squared and g of x equals 2x, then f plus g of x equals x squared plus 2x. Subtraction works similarly. F minus g of x equals f of x minus g of x. The domain is the intersection of the individual domains. Remember that order matters here. F minus g is not the same as g minus f. The difference changes sign when you reverse the order. For multiplication, we have f times g of x equals f of x times g of x. We can also multiply a function by a scalar, k times f of x equals k times f of x, where k is any real number. The domain is again the intersection of domains. This is called pointwise multiplication. Division of functions is f divided by g of x equals f of x divided by g of x. But there's an important condition: g of x must not equal 0. so we must exclude any points where the denominator function equals 0. The domain is the intersection of domains minus all points where g of x is 0. Let's summarize Chapter 2. We learned about ordered pairs and Cartesian products, the foundation of relations. Relations are subsets of Cartesian products that connect elements between sets. Functions are special relations where each element has exactly one image. We studied various function types: identity, polynomial, rational, modulus, signum, and greatest integer functions. Finally, we learned how to add, subtract, multiply, and divide functions. Thank you for joining Chapter 2 on Relations and Functions. Welcome to Chapter 3, Trigonometric Functions. The word trigonometry comes from Greek words meaning measuring the sides of a triangle. Originally developed for navigation and surveying, today trigonometry is used in seismology, electric circuit design, music analysis, and many other fields. In this chapter, we'll extend trigonometric ratios to work with any angle. Let's understand what an angle really is. An angle measures the rotation of a ray about its initial point. The original position is called the initial side, and the final position after rotation is the terminal side. If rotation is anti-clockwise, the angle is positive. If clockwise, the angle is negative. The most familiar unit for measuring angles is the degree. One complete revolution equals 360 degrees. Each degree is divided into 60 minutes and each minute into 60 seconds. A quarter revolution is 90 degrees, a half is 180 degrees, and a full turn is 360 degrees. There's another important unit called the radian. In a unit circle with radius 1, an arc of length 1 subtends an angle of 1 radian at the center. One complete revolution equals 2 pi radians. The key formula is angle in radians equals arc length divided by radius. Converting between degrees and radians is essential. Pi radians equals 180 degrees, so 1 radian is approximately 57 degrees 16 minutes. To convert degrees to radians, multiply by pi over 180. To convert radians to degrees, multiply by 180 over pi. Key conversions to memorize: 30 degrees is pi over 6, 45 degrees is pi over 4, 60 degrees is pi over 3, and 90 degrees is pi over 2. Now let's define trigonometric functions using the unit circle. Consider a unit circle with center at the origin. For any point P with coordinates a, b on the circle, making an angle x with the positive x-axis, we define cos x equals a and sin x equals b. The x-coordinate gives cosine and the y-coordinate gives sine. Since every point on the unit circle satisfies a squared plus b squared equals 1, we get the fundamental trigonometric identity: cos squared x plus sine squared x equals 1. This is also called the Pythagorean identity, and it forms the basis for many other trigonometric identities. From sine and cosine, we define the other 4 trigonometric functions. Tangent is sine divided by cosine. Cosecant is 1 over sine. Secant is 1 over cosine. Cotangent is cosine divided by sine. Each has domain restrictions where the denominator equals 0. The signs of trigonometric functions depend on the quadrant. In quadrant 1, all functions are positive. In quadrant 2, sine and cosecant are positive. In quadrant 3, tangent and cotangent are positive. In quadrant 4, cosine and secant are positive. Remember the mnemonic ASTC, all, sin, tan, cos, for quadrants 1, 2, 3, 4. Let's discuss domain and range. Sine and cosine have domain all real numbers and range from -1 to 1. Tangent has domain all real numbers except odd multiples of pi over 2 and range all real numbers. Cosecant and secant have ranges from -infinity to -1 and from 1 to infinity. Now for the sum and difference formulas. Cosine of x plus y equals cos x cos y minus sin x sin y. Cosine of x minus y equals cos x cos y plus sin x sin y. Sin of x plus y equals sin x cos y plus cos x sin y. Sin of x minus y equals sin x cos y minus cos x sin y. These are fundamental identities you'll use constantly. Tangent sum and difference formulas are tan of x plus y equals tan x plus tan y, all divided by 1 minus tan x times tan y. Tan of x minus y equals tan x minus tan y divided by 1 plus tan x times tan y. Similar formulas exist for cotangent using the same pattern. Double angle formulas are very useful. Sine of 2x equals 2 sin x cos x. Cosine of 2x can be written 3 ways: cos squared x minus sine squared x, or 2 cos squared x minus 1, or 1 minus 2 sine squared x. Tangent of 2x equals 2 tan x divided by 1 minus tan squared x. Complementary angles add to 90 degrees or pi over 2 radians. The key formulas are sine of pi over 2 minus x equals cos x, and cosine of pi over 2 minus x equals sine x. Similarly, tangent of pi over 2 minus x equals cot x. These show how complementary angles swap sine and cosine. Supplementary angles add to 180 degrees or pi radians. Sine of pi minus x equals sine x, but cosine of pi minus x equals negative cos x. Tangent of pi minus x equals negative tan x. For pi plus x, both sine and cosine become negative. Sine of pi plus x equals negative sine x. Cosine of pi plus x equals negative cos x. Two important related identities are 1 plus tan squared x equals sec squared x, and 1 plus cot squared x equals cosec squared x. These are derived from the fundamental identity by dividing both sides by cos squared x or sine squared x, respectively. They're essential for solving trigonometric equations. Trigonometric functions are periodic. Their values repeat at regular intervals. Sine and cosine repeat every 2 pi radians, so their period is 2 pi. Tangent repeats every pi radians, so its period is pi. Secant and cosecant have period 2 pi, while cotangent has period pi. You must memorize values at standard angles. At 0 degrees, sine is 0 and cos is 1. At 30 degrees, sin is 1 over 2 and cos is root 3 over 2. At 45 degrees, both sin and cos are 1 over root 2. At 60 degrees, sin is root 3 over 2 and cos is 1 over 2. At 90 degrees, sin is 1 and cos is 0. Negative angle formulas show how functions behave with negative inputs. Sine of negative x equals negative sine x, making sine an odd function. Cosine of negative x equals cos x, making cosine an even function. Tangent of negative x equals negative tan x, so tangent is also odd. The reciprocal functions follow the same pattern. Understanding the graphs of trigonometric functions is crucial. The sine graph is a wave oscillating between -1 and 1, completing one cycle every 2 pi. Cosine looks similar but starts at 1 instead of 0. The tangent graph is unbounded with vertical asymptotes at pi over 2, 3 pi over 2, and so on. Trigonometry has countless real-world applications. Navigation uses it to find positions and directions. Surveying relies on it to measure distances and heights. Engineers use it in structural design. Physicists apply it to study wave motion and oscillations. Even music analysis uses trigonometric functions to understand sound waves. Here are some problem-solving tips. Always convert angles to the same unit before calculating. Use identities to simplify complex expressions. Check which quadrant your angle lies in to determine the correct sign. Use periodicity to reduce large angles to smaller, manageable ones within the first revolution. Watch out for common mistakes. Don't confuse sin squared x with sin of x squared. They're completely different. Be careful with signs when applying quadrant rules. Remember that tan, sec, cosec, and cot have domain restrictions where they're undefined. Double-check your application of sum and difference formulas. Let's summarize the key formulas. The fundamental identity is cos squared x plus sine squared x equals 1. The sum formulas are sine of x plus y equals sine x cos y plus cos x sine y, and cos of x plus y equals cos x cos y minus sine x sine y. The double angle formulas are sine 2x equals 2 sine x cos x, and cos 2x equals cos squared x minus sine squared x. In this chapter, we learned that angles can be measured in degrees or radians. We defined 6 trigonometric functions using the unit circle. The fundamental identity, cos squared x plus sine squared x equals 1, leads to many other identities. We studied sum, difference, and double angle formulas. We also learned about periodicity and sign rules based on quadrants. Thank you for joining Chapter 3 on trigonometric functions. Welcome to Chapter 4, complex numbers and quadratic equations. We know that x squared plus 1 equals 0 has no real solution since squares are always non-negative. To solve such equations, we extend the real number system to include complex numbers. This powerful extension, developed by W.R. Hamilton, allows us to solve all quadratic equations. A complex number has the form z equals a plus ib, where a and b are real numbers. Here, a is called the real part, written rez, and b is called the imaginary part, written imz. The symbol I is the imaginary unit, defined by the property that I squared equals -1. Two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So if z1 equals a plus ib and z2 equals c plus id, then z1 equals z2 precisely when a equals c and b equals d. This is a fundamental property we use constantly. Adding complex numbers is straightforward. Add real parts and imaginary parts separately. If z1 equals a plus ib and z2 equals c plus id, then z1 plus z2 equals a plus c plus I times b plus d. Addition is commutative and associative. The additive identity is 0 plus I0, and every complex number has an additive inverse. Multiplication uses the rule I squared equals -1. The product of a plus ib and c plus id equals ac minus bd plus I times ad plus bc. Multiplication is also commutative and associative, has identity 1 plus I0, and every non-zero complex number has a multiplicative inverse. The powers of I follow a beautiful pattern. I squared is -1, I cubed is I to the fourth is 1. Then the pattern repeats. I to the fifth is I to the sixth is -1, and so on. In general, I to the power 4k is 1, I to the power 4k plus 1 is I to the power 4k plus 2 is -1, and I to the power 4k plus 3 is I. We can now take square roots of negative numbers. The square root of -1 is I. More generally, the square root of -a, where a is positive, equals I times the square root of a. For example, the square root of -3 equals I times root 3. Both I and -I are square roots of -1. The modulus of a complex number z equals a plus ib is defined as the square root of a squared plus b squared. We write it as z. It represents the distance from the origin in the complex plane. For example, the modulus of 3 plus 4i is the square root of 9 plus 16, which equals 5. The conjugate of a complex number z equals a plus ib is z bar equals a minus ib. We simply change the sign of the imaginary part. Important properties. Z times z bar equals z squared. Z plus z bar equals 2a, which is twice the real part. Z minus z bar equals 2ib, which is 2i times the imaginary part. Division of complex numbers uses the conjugate. To divide z1 by z2, we multiply both numerator and denominator by z2 bar. This gives us z1 times z2 bar divided by z2 squared. The denominator becomes a real number, making the result easy to express in standard form a plus ib. The Argand plane provides a geometric representation of complex numbers. The x-axis represents the real part, and the y-axis represents the imaginary part. A complex number a plus ib corresponds to the point AB in this plane. This visual representation helps us understand operations like addition and multiplication geometrically. Complex numbers can also be written in polar form. Z equals r times cos theta plus I sine theta, where r is the modulus and theta is the argument, the angle from the positive x-axis. This is also called the modulus argument form. Euler's formula connects this to exponentials. E to the power I theta equals cos theta plus I sin theta. Now we can solve quadratic equations with negative discriminants. For x squared plus bx plus c equals 0, the discriminant d equals b squared minus 4ac. When d is negative, the solutions are complex. We use the quadratic formula x equals -b plus or minus the square root of d, all divided by 2a. The square root of -d becomes I times root d. Let's solve x squared plus x plus 1 equals 0. The discriminant is 1 minus 4, which equals -3. Since d is negative, we have complex roots. Using the quadratic formula, x equals -1 plus or minus I times root 3, all divided by 2. These are two complex conjugate roots. Important properties of conjugates and modulus. The modulus of a product equals the product of moduli. The modulus of a quotient equals the quotient of moduli. The conjugate of a sum equals the sum of conjugates. The conjugate of a product equals the product of conjugates. These properties simplify many calculations. Standard algebraic identities work for complex numbers too. The square of a sum, z1 plus z2, squared equals z1 squared plus z2 squared plus 2z1 z2. The square of a difference, z1 minus z2, squared equals z1 squared minus 2z1 z2 plus z2 squared. And the difference of squares, z1 squared minus z2 squared equals z1 plus z2 times z1 minus z2. The multiplicative inverse of z equals a plus ib is 1 over z equals z bar over z squared. This equals a minus ib divided by a squared plus b squared. In standard form, a over a squared plus b squared minus I times b over a squared plus b squared. We find this by multiplying numerator and denominator by the conjugate. Complex numbers have countless applications. In electrical engineering, they analyze AC circuits using impedance. In quantum mechanics, wave functions are complex valued. Signal processing uses complex numbers for Fourier transforms. Control systems use them for stability analysis. They're essential tools in modern science and engineering. Watch out for common mistakes. Never write square root of negative 1 times square root of negative 1 equals square root of 1 equals 1. This is wrong. Remember that square root of negative a equals I times root a, not negative root a. And I squared equals negative 1, not 1. The conjugate only changes the sign of the imaginary part. Here are the key formulas to remember. I squared equals negative 1. A complex number z equals a plus ib has modulus z equal to the square root of a squared plus b squared. Its conjugate z bar equals a minus ib. The product z times z bar equals z squared. And the quadratic formula works for complex roots when the discriminant is negative. When solving problems with complex numbers, use conjugates to simplify expressions. Use modulus properties for multiplication and division. Convert to polar form when dealing with powers. Always check the discriminant to determine if a quadratic has real or complex roots. To find powers of I, divide the exponent by 4 and use the remainder. For I to the 17th power, 17 equals 4 times 4 plus 1, so the remainder is 1, giving I. For I to the 100th power, 100 equals 4 times 25 plus 0, so the remainder is 0, giving 1. For negative powers, I to the minus n equals 1 over I to the n. Geometrically, addition of complex numbers is vector addition in the Argand plane. The modulus represents distance from the origin. The conjugate is the reflection in the real axis. Multiplication by a complex number involves both scaling and rotation. The modulus scales by the product of moduli, and the angle adds. Real numbers are complex numbers with zero imaginary part. They're of the form a plus 0i. Purely imaginary numbers have zero real part. They're of the form 0 plus bi. Real numbers are a subset of complex numbers. Complex numbers complete our number system, allowing us to solve any polynomial equation. In this chapter, we learn that complex numbers extend the real numbers to solve equations like x squared plus 1 equals 0. A complex number has the form a plus ib with real part a and imaginary part b. We studied addition, subtraction, multiplication, and division of complex numbers. The modulus and conjugate are key concepts. Quadratic equations can have complex roots when the discriminant is negative. Thank you for joining Chapter 4 on complex numbers and quadratic equations. Welcome to Chapter 5, Linear Inequalities. Not all mathematical problems can be expressed as equations. Inequalities use symbols like less than, greater than, less than or equal, and greater than or equal. They're essential in science, statistics, economics, and psychology. For example, saying height is less than 160 centimeters or at most 60 chairs uses inequalities. An inequality relates two numbers or expressions using less than, greater than, or the equal or versions. Numerical inequalities compare numbers like 3 is less than 5. Literal inequalities involve variables like x is less than 5. Double inequalities like 3 is less than x is less than 5 mean x lies between 3 and 5. Inequalities come in different types. Strict inequalities use less than or greater than. The boundary is not included. Slack inequalities use less than or equal or greater than or equal. The boundary is included. Linear inequalities in one variable have the form ax plus b less than 0. In two variables, they're like a x plus by less than c. A solution of an inequality is a value that makes it true. For example, in 30x less than 200, the values x equals 0, 1, 2, 3, 4, 5, and 6 all work. The solution set is 0, 1, 2, 3, 4, 5, 6. These are all values that satisfy the inequality. Here are the key rules for solving inequalities. Rule 1. You can add or subtract the same number from both sides without changing the inequality sign. Rule 2. Multiplying or dividing by a positive number keeps the sign the same. But here's the crucial one. Rule 2b. When you multiply or divide by a negative number, you must reverse the inequality sign. For example, 3 is greater than 2 becomes negative, 3 is less than negative 2. To solve a linear inequality in one variable, isolate the variable just like solving an equation, but watch carefully for sign reversal when multiplying by a negative. For example, solve 5x minus 3 is less than 3x plus 1. Subtract 3x from both sides. 2x minus 3 is less than 1. Add 3, 2x is less than 4. Divide by 2, x is less than 2. We represent solutions on a number line. For x is less than 3, draw an open circle at 3 and shade everything to the left. The open circle means 3 is not included. For x is less than or equal to 3, use a closed or filled circle. This means 3 is included in the solution. Solution sets depend on what domain we're working in. In natural numbers, solutions are positive integers like 1, 2, 3. In integers, we include negatives and 0. In real numbers, we use interval notation. For example, x is less than 2 in real numbers is written as the open interval from negative infinity to 2. Interval notation is a compact way to write solution sets. Open interval AB means A is less than x is less than b minus endpoints not included. Closed interval AB means A is less than or equal to x is less than or equal to b endpoints included. Half-open intervals like AB mix these. Unbounded intervals use infinity symbols. Word problems require translating words into inequality symbols. At least means greater than or equal to. At most means less than or equal to. More than means greater than. Less than means less than. Read carefully, identify your variable, and write the inequality that captures the condition. Linear inequalities in two variables have the form ax plus by less than c. The solution is not a single value, but an entire region in the coordinate plane. The boundary line ax plus by equals c divides the plane into two half-planes. One half-plane contains all the solutions. To graph a two-variable inequality, first draw the boundary line. Use a solid line for less than or equal to or greater than or equal to, the boundary is included. Use a dashed line for strict inequalities, the boundary is excluded. Then test a point to determine which side to shade. Testing points is simple. Pick a point not on the line. The origin 0, 0 is easiest if the line doesn't pass through it. Substitute the coordinates into the inequality. If it makes the inequality true, shade that side. If false, shade the opposite side. Let's graph 2x plus y is less than 4. First, draw the boundary line 2x plus y equals 4 as a dashed line since the inequality is strict. Test the origin. 0 plus 0 is less than 4, which is true. So shade the half-plane containing the origin. All points in the shaded region satisfy the inequality. Systems of linear inequalities involve two or more inequalities in two variables. The solution is the intersection of all the regions, where all inequalities are satisfied simultaneously. Graph each inequality separately, then identify the overlapping region. This intersection is your solution set. Linear inequalities have many real-life applications. In economics, they model budget constraints. In resource allocation, they show available resources. Optimization problems use them to define feasible regions. Manufacturing uses them for production planning. They're essential tools in operations research. Watch out for common mistakes. The biggest one is forgetting to reverse the inequality sign when multiplying by a negative number. Also, use solid lines for inclusive inequalities and dashed lines for strict ones. Always test a point to make sure you're shading the correct side. Check whether the boundary is included. Here's a problem-solving strategy. First, read the problem carefully and identify your variable. Translate the words into inequality symbols. Remember, at least means greater than or equal. Solve the inequality algebraically. Finally, verify that your solution makes sense in the context of the original problem. Let's summarize the key rules. Adding or subtracting the same number from both sides doesn't change the sign. Multiplying or dividing by a positive number keeps the sign. Multiplying or dividing by a negative number reverses the sign. Division follows the same rules as multiplication. Some graphing tips. Always test a point to verify you're shading the correct side. The origin 0, 0 is the easiest test point, but first check that the boundary line doesn't pass through it. Label your boundary lines clearly with their equations. Remember, solid line means included, dashed line means excluded. Double inequalities have the form a is less than x is less than b, meaning x lies between a and b. Solve them as two separate inequalities and find the intersection. For example, 3 is less than 2x minus 1 is less than 7. First, 3 is less than 2x minus 1 gives x is greater than 2. Second, 2x minus 1 is less than 7 gives x is less than 4. Combined, 2 is less than x is less than 4. Compound inequalities use and or connectors. With and, both conditions must be true. Find the intersection of solutions. With or, at least one condition must be true. Find the union of solutions. Graph accordingly on the number line. The connector type determines the solution set. Here's a real-world example. A student scores 62 and 48 on 2 exams. She needs an average of at least 60. Let x be her third exam score. The average is 62 plus 48 plus x divided by 3. This must be greater than or equal to 60. Solving. 110 plus x is greater than or equal to 180, so x is greater than or equal to 70. She needs at least 70 on the third exam. For consecutive odd number problems, remember that consecutive odd numbers differ by 2. If x is the smaller, the next is x plus 2. Apply the given conditions as inequalities, then find valid integer solutions. For example, finding consecutive odd natural numbers both greater than 10 with sum less than 40 gives the pairs 11, 13, 13, 15, 15, 17, and 17, 19. In this chapter, we learned that inequalities express ranges rather than exact values. The key rule is to reverse the inequality sign when multiplying by a negative number. For one variable, solutions are shown on a number line. For two variables, solutions are half-planes in the coordinate plane. Inequalities have important applications in optimization and constraint problems. Thank you for joining Chapter 5 on linear inequalities. Welcome to Chapter 6, Permutations and Combinations. We'll learn fundamental counting techniques to determine the number of ways to arrange and select objects without actually listing them. These techniques have practical applications like figuring out lock combinations, passwords, and signals. This branch of mathematics was developed by Jacob Bernoulli in the 17th century. The fundamental principle of counting is simple but powerful. If one event can occur in m ways and another event can occur in n ways, then both events together can occur in m times n ways. For example, if you have 3 pants and 2 shirts, you can create 3 times 2 equals 6 different outfits. This is also called the multiplication principle. We can extend this principle to more events. For 3 events occurring in m and p ways respectively, the total is m times n times p. For example, choosing from 2 school bags, 3 tiffin boxes, and 2 water bottles gives 2 times 3 times 2 equals 12 different combinations. For k events, simply multiply all the possibilities together. The counting principle has many applications. We can find the number of words formed from letters, the number of signals from flags, the number of possible outcomes in experiments, and the number of arrangements of objects. Anytime you need to count possibilities without listing them all, this principle helps. Let's work through an example. How many 4-letter words can we form from the letters of rows without repetition? The first position has 4 choices, the second has 3 remaining choices, the third has 2, and the last has 1. By the multiplication principle, 4 times 3 times 2 times 1 equals 24 different words. A permutation is an arrangement in a definite order. The key point is that order matters. ABC is different from BAC. We denote the number of permutations of n objects taken r at a time as npr. For example, arranging 3 people in a line from a group of 5 is a permutation. The permutation formula is npr equals m's n minus n minus 2 all the way to nr plus 1. This counts ways to arrange r items. The first choice has n from m n options, the second has n minus 1, and so on. For example, 5p3 equals 5 times 4 times 3 equals 60 arrangements. Factorial notation makes formulas cleaner. N factorial, written n, equals n times n1 times n2, all the way down to 2 times 1. We read this as n factorial. By definition, 0 factorial equals 1. An important property, n factorial equals n times n1 factorial. Using factorials, the permutation formula becomes np equals n factorial divided by n minus r factorial. For example, 5p3 equals 5 factorial divided by 2 factorial, which is 120 divided by 2, giving 60. When r equals n, we get npn equals n factorial, arranging all n objects. When repetition is allowed, each position has n choices, giving n to the power r total arrangements. For example, forming 3-digit numbers from digits 1 through 5. With repetition, we get 5 cubed equals 125 numbers. Without repetition, we get 5p3 equals 60 numbers. The difference is significant. A combination is a selection where order does not matter. ABC and BAC are the same combination because they contain the same elements. We denote combinations as NCR or C of NR. Choosing 3 people from a group of 5 for a committee is a combination. The order of selection doesn't matter. The combination formula is NCR equals n factorial divided by r factorial times nr factorial. The relationship with permutations, NCR equals NPR divided by r factorial. For example, 5C3 equals 5 factorial divided by 3 factorial times 2 factorial, which equals 10 ways to choose 3 from 5. Combinations have important properties. The symmetry property, NCR equals NCNR, also equals NCN equals 1. Pascal's identity states that NCR plus NCR minus 1 equals NCR. These properties are fundamental to the binomial theorem and appear throughout probability theory. The key difference, permutations count arrangements where order matters. Combinations count selections where order doesn't matter. The relationship is NPR equals NCR times r factorial. Think of it as first choose r items, combination, then arrange them r factorial ways. Here are practical examples to distinguish them. Arranging books on a shelf, permutation, order matters. Selecting committee members, combination, order doesn't matter. Forming words from letters, permutation. Choosing cards from a deck, combination. Always ask, does changing the order create a different outcome? When objects are identical, we adjust our counting. For n objects, where p are identical, the number of distinct arrangements is n factorial divided by p factorial. For example, arrangements of Mississippi, we divide by factorials of the counts of each repeated letter. The word has 11 letters with various repetitions. Circular permutations count arrangements in a circle. For n objects arranged in a circle, the number is n1 factorial. Why? Because rotating the circle doesn't create a new arrangement. The trick? Fix one object in place, then arrange the remaining n-1 objects. Real-life applications are everywhere. Password security depends on counting possible combinations. Team selections use combinations. Tournament scheduling uses permutations. Probability calculations frequently involve both. These concepts are essential in computer science, statistics, and operations research. Watch out for common mistakes. Don't confuse permutations with combinations. Always check if order matters. When objects repeat, remember to divide by the appropriate factorials. Read problems carefully for restrictions. Make sure you're applying the fundamental principle correctly to each situation. Here are the key formulas to memorize. NPR equals n factorial divided by nr factorial for permutations. NCR equals n factorial divided by r factorial times nr factorial for combinations. With repetition allowed, use n to the power r. For circular arrangements, use ne1 factorial. When solving problems, first identify whether order matters. That tells you permutation or combination. Check if repetition is allowed. Look for special restrictions like must include or cannot be together. Then apply the appropriate formula and calculate carefully. Here's a committee selection example. Select 3 people from 5 men and 4 women with exactly 2 men and 1 woman. Choose 2 men from 5, that's 5C2 equals 10 ways. Choose 1 woman from 4, that's 4C1 equals 4 ways. Total, 10 times 4 equals 40 ways. This is a combination problem. Let's arrange 5 different books on a shelf where 2 particular books must stay together. Treat those 2 books as one unit. Now we have 4 items to arrange. 4 factorial equals 24 ways. But the 2 books can be arranged among themselves in 2 factorial equals 2 ways. Total, 24 times 2 equals 48 arrangements. Pascal's triangle is deeply connected to combinations. The values of NCR form the triangle's entries. Each entry is the sum of the 2 entries above it. This appears in binomial expansion coefficients. The triangle provides a quick way to find combination values without calculating factorials. In this chapter, we learned the fundamental principle of counting. Multiply possibilities for sequential events. Permutations count arrangements where order matters, using NPR equals n factorial over nr factorial. Combinations count selections where order doesn't matter, using NCR equals n factorial over r factorial times nr factorial. Factorial notation simplifies these expressions. These concepts have countless real-world applications. Thank you for joining Chapter 6 on Permutations and Combinations. Welcome to Chapter 7, the Binomial Theorem. This powerful theorem gives us an easy way to expand expressions like a plus b to the power n without doing repeated multiplication. It's based on patterns discovered by Blaise Pascal in the 17th century. The theorem makes calculating high powers practical. Let's start with simple binomial expansions. A plus b to the 0 equals 1. A plus b to the 1 equals a plus b. A plus b squared equals a squared plus 2ab plus b squared. A plus b cubed equals a cubed plus 3a squared, b plus 3ab squared plus b cubed. Notice the patterns forming. Key patterns emerge in binomial expansions. The number of terms is always one more than the index, so a plus b to the n has n plus 1 terms. Powers of a decrease by 1 in each successive term. Powers of b increase by 1, and importantly, the sum of the indices of a and b equals n in every term. Pascal's triangle is a beautiful arrangement of numbers. Each row gives the coefficients for expanding a plus b to the n. The triangle starts with 1 at the top. Each number below is the sum of the two numbers above it. Every row starts and ends with 1. This pattern continues indefinitely. We can express Pascal's triangle using combination notation. Row n contains NC0, NC1, NC2, all the way to NCn. Remember, NCR equals n factorial divided by r factorial times n minus r factorial. For example, row 5 gives us 5C0, 5C1, 5C2, 5C3, 5C4, 5C5, which equals 1, 5, 10, 10, 5, 1. The binomial theorem states, a plus b to the n equals NC0 times a to the n, plus NC1 times a to the n minus 1 times b, plus NC2 times a to the n minus 2 times b squared, continuing until NCn times b to the n. The general term is t subscript r plus 1 equals NCR times a to the n minus r times b to the r. This is proven using mathematical induction. Let's expand x plus 2 to the 6. Using the theorem, 6c0 times x to the 6 plus 6c1 times x to the 5 times 2 plus 6c2 times x to the 4 times 4, and so on. This gives us x to the 6 plus 12x to the 5 plus 60x to the 4 plus 160x cubed plus 240x squared plus 192x plus 64. The binomial coefficients are 1, 6, 15, 20, 15, 6, 1. For x minus y to the n, we replace b with negative y. The expansion becomes nc0 times x to the n minus nc1 times x to the n minus times y plus nc2 times x to the n minus 2 times y squared, and so on. The signs alternate, plus minus plus minus. The sign of term r is negative 1 to the r. A special case, 1 plus x to the n. Setting a equal to 1 and b equal to x, we get nc0 plus nc1 times x plus nc2 times x squared, continuing to ncn times x to the n. For x equals 1, this gives us 2 to the n equals the sum of all binomial coefficients. This is a fundamental identity. Another special case, 1 minus x to the n. Setting a equal to 1 and b equal to negative x, we get alternating signs. For x equals 1, the alternating sum equals 0, nc0 minus nc1 plus nc2 minus equals 0. This identity is useful in many mathematical proofs. To find specific terms, use the general term formula. T subscript r plus 1 equals ncr times a to the n minus r times b to the r. The first term, t1, equals a to the n. The last term, t subscript n plus 1 equals b to the n. Middle terms depend on whether n is even or odd. To find the coefficient of x to the r in a plus bx to the n, use the general term. It's ncr times a to the n minus r times bx to the r. So the coefficient is ncr times a to the n minus r times b to the r. For example, finding the coefficient of x cubed in 1 plus 2x to the 5. Finding middle terms, if n is even, there's one middle term, t subscript n over 2 plus 1. If n is odd, there are two middle terms, t subscript n plus 1, 2, and t subscript n plus 3 verse 2. For example, a plus b to the 4 has middle term t3. A plus b to the 5 has middle terms t3 and t4. Numerical applications are powerful. To calculate 98 to the 5, write it as 100 minus 2 to the 5. Use the binomial expansion. This is much easier than direct multiplication. Another example, 1.01 to the 100 is greater than 100, which we can prove using just the first few terms. Important properties of binomial coefficients. The sum nc0 plus nc1 plus ncn equals 2 to the n. The alternating sum nc0 minus nc1 plus nc2 minus equals 0. Symmetry. nck equals ncn minus k. These properties follow from setting x equal to 1 or x equal to negative 1 in special cases. The greatest binomial coefficient depends on n. For n even, NCN2 is the greatest. For n odd, NCN-1, 2, and NCN+1, 2 are equal and greatest. The coefficients increase to the middle, then decrease symmetrically. This pattern is visible in Pascal's triangle. The binomial theorem helps prove divisibility. For example, proving 6 to the n-5n leaves remainder 1 when divided by 25. Write 6 to the n as 1 plus 5 to the n. Expand using the binomial theorem. Extract terms divisible by 25. The remainder is indeed 1. Approximations use the binomial theorem. For small x, 1 plus x to the n is approximately 1 plus nx. The first two terms are often sufficient for good approximations. This is used throughout physics and engineering. For example, 1.01 to the 100 is approximately 1 plus 100 times 0.01, which equals 2. Watch out for common mistakes. Don't forget the alternating signs in x minus y to the n. When finding a specific term, be careful with the term number. The rth term uses NCR-1. Simplify coefficients properly. Remember, the coefficient is just the number, not including the variables. Key formulas to remember. A plus b to the n equals the sum from r equals 0 to n of NCR times a to the n minus r times b to the r. The general term is t subscript r plus 1 equals NCR times a to the n minus r times b to the r. The sum of all coefficients equals 2 to the n. The alternating sum equals 0. Problem-solving strategy. First, identify which form you have, a plus b to the n, a minus b to the n, or 1 plus x to the n. Determine which term you need. Apply the general term formula. Simplify carefully, watching for signs and powers. Let's find the fifth term in 2x plus 3 to the 7. t5 equals t subscript 4 plus 1, so r equals 4. Using the formula, 7c4 times 2x to the 7 minus 4 times 3 to the 4. That's 7c4 times 2x cubed times 81. Calculate. 35 times 8x cubed times 81 equals 2206 to 80 or x cubed. Find the coefficient of x to the 10 in x squared plus 1x to the 20. The general term is t subscript, r plus 1, equals 20cr times x squared to the 20 minus r times 1x to the r. Simplifying, 20cr times x to the 40 minus 2r times x to the minus r equals 20cr times x to the 40 minus 3r. For x to the 10, 40 minus 3r equals 10, so r equals 10. The coefficient is 20c10. The binomial theorem connects to probability through the binomial distribution. The probability of exactly r successes in n independent trials is p of r equals NCR times p to the r times 1 minus p to the n minus r. The binomial coefficients are fundamental to probability theory. This is one of the most important distributions in statistics. In this chapter, we learned that the binomial theorem efficiently expands a plus b to the n. Pascal's triangle provides the coefficients visually. The general term is t subscript r plus 1 equals NCR times a to the n minus r times b to the r. Special cases like 1 plus x to the n simplify many problems. Applications range from approximations to divisibility proofs. Thank you for joining Chapter 7 on the binomial theorem. Welcome to Chapter 8, Sequences and Series. A sequence is an ordered collection of objects with a first member, second member, and so on. Sequences appear everywhere: population counts over time, bank deposits over years, and depreciating values. The famous Fibonacci sequence dates back to 1175. When sequences follow specific patterns, we call them progressions. What exactly is a sequence? It's an ordered list where each element has a position, first, second, third, and so on. We denote terms as A1, A2, A3, up to an, where the subscript indicates position. The nth term, called the general term, is the most important for finding patterns. Sequences can be finite or infinite. A finite sequence has a fixed number of terms, like counting ancestors over 300 years, which gives exactly 10 generations. An infinite sequence never ends, like the successive quotients when dividing 10 by 3, which continues forever. We can often find a formula for the nth term. For even numbers 2, 4, 6, 8, the nth term is an equals 2n. For odd numbers 1, 3, 5, 7, the nth term is an equals 2n minus 1. However, some sequences like the prime numbers 2, 3, 5, 7, 11 have no simple formula. The Fibonacci sequence is famous: 1, 1, 2, 5, 8, 13, 21, and so on. Each term is the sum of the two preceding terms. The recurrence relation is an equals an2 plus an1. This sequence appears throughout nature, in flower petals, pine cones, and shell spirals. A series is the sum of terms of a sequence. We write it as A1 plus A2 plus A3 and so on. The sigma notation uses the Greek letter sigma to indicate summation compactly, sum from k equals 1 to n of ak. Series can be finite or infinite, just like sequences. An arithmetic progression, or AP, is a sequence where each term differs from the previous by a constant. The form is a plus d, a plus 2d, a plus 3d, and so on. Here, a is the first term and d is the common difference. For example, 3, 7, 11, 15, 19 has d equal to 4. The nth term of an AP is given by an equals a plus n minus 1 times d. The first term is a1 equals a. The last term, L equals a plus n minus 1 times d. For example, the 10th term of the sequence 2, 5, 8, 11 is 2 plus 9 times 3 equals 29. The sum of n terms of an AP has two formulas. Sn equals n over 2 times 2a plus n minus 1d. Alternatively, Sn equals n over 2 times a plus L, where L is the last term. For the sum of first n natural numbers, we get n times n plus 1 over 2. Sum of 1 to 10 equals 10 times 11 over 2 equals 55. The arithmetic mean between two numbers a and b is simply a plus b over 2. We can insert n arithmetic means between a and b, creating an arithmetic progression. The common difference becomes d equals b minus a over n plus 1. A geometric progression, or GP, is a sequence where each term is a constant multiple of the previous term. The form is ar squared, ar cubed, and so on. Here, a is the first term, and r is the common ratio. For example, 2, 6, 18, 54 has r equal to 3. The nth term of a GP is an equals a times r to the power n minus 1. The first term is a1 equals a. The last term, L equals a times r to the power n minus 1. For example, the fifth term of 3, 6, 12, 24 is 3 times 2 to the fourth power equals 48. The sum of n terms of a GP depends on r. If r equals 1, then Sn equals Na. If r is not 1, then Sn equals a times r to the n minus 1 over r minus 1. An alternative form is Sn equals a times 1 minus r to the n over 1 minus r. For 2, 4, 8, 16, the sum is 2 times 16 minus 1 over 2 minus 1 equals 30. The geometric mean between two positive numbers a and b is the square root of a times b. We can insert n geometric means between a and b, creating a geometric progression. The common ratio becomes r equals b over a to the power 1 over n plus 1. An important relationship. For any two positive numbers a and b, the arithmetic mean is always greater than or equal to the geometric mean. Equality holds only when a equals b. The difference am minus gm equals square root of a minus square root of b squared, all divided by 2. Special series formulas are worth memorizing. The sum of first n natural numbers is n times n plus 1 over 2. The sum of squares is n times n plus 1 times 2n plus 1 over 6. The sum of cubes is n times n plus 1 over 2 all squared. These appear frequently in problems. For infinite geometric series, when the absolute value of r is less than 1, the sum converges to a over 1 minus r. If the absolute value of r is greater than or equal to 1, the series diverges. For example, 1 plus 1 half plus 1 fourth plus equals 1 over 1 minus 1 half equals 2. Real-life applications are everywhere. Compound interest uses geometric progressions. Population growth often follows geometric patterns. Radioactive decay decreases geometrically. Loan amortization schedules use arithmetic progressions for principal payments. Avoid common mistakes. Don't confuse AP with GP. Check whether terms have constant difference or constant ratio. Use the correct sum formula for each. For infinite series, always verify that the absolute value of r is less than 1. Watch for sign errors in the common difference. Key formulas to remember. For AP, the nth term is a plus n minus 1d, and the sum is n over 2 times 2a plus n minus 1d. For GP, the nth term is a times r to the n minus 1, and the sum is a times r to the n minus 1 over r minus 1. Problem-solving strategy. First, identify whether the sequence is an AP or GP by checking for constant difference or constant ratio. Find the first term and the common difference or ratio. Apply the appropriate formula. Determine if the sum is finite or infinite. Let's find the sum of 3, 7, 11, up to 20 terms. This is an AP with a equals 3, d equals 4, and n equals 20. Using the formula, S20 equals 20 over 2 times 3 plus 19 times 4. That's 10 times 6 plus 76 equals 10 times 82 equals 820. Each term of 2, 832 equals 131072. This is a GP with A equals 2 and R equals 4. We need N such that N equals 131072. So 2 times 4 to the N minus 1 equals 31072. Dividing by 2, 4 to the N minus 1 equals 65,536, which is 4 to the 8th. Therefore, N minus 1 equals 8, so N equals 9. An arithmetic geometric series has each term as a product of AP and GP terms. For example, 1 plus 2x plus 3x squared plus 4x cubed and so on. To sum such series, use a special technique. Multiply by the common ratio and subtract from the original series. In this chapter, we learned that sequences are ordered lists of numbers. An arithmetic progression has a constant difference between terms, while a geometric progression has a constant ratio. We derived important formulas for the nth term and sum of each type. These concepts have wide applications in finance, science, and nature. Thank you for joining Chapter 8 on sequences and series. Welcome to Chapter 9, straight lines. This chapter combines algebra and geometry in what we call analytical geometry. The French mathematician René Descartes pioneered this approach in his 1637 book, La Géométrie. By representing geometric figures with equations, we can solve geometric problems algebraically. The straight line is the simplest yet most fundamental geometric figure. Coordinate geometry basics. The xy plane has two perpendicular axes, the x-axis running horizontally and the y-axis running vertically. Every point is located by its coordinates, x, y, where x is the horizontal distance from the origin and y is the vertical distance. We can calculate distances between points and find points that divide line segments. The distance formula gives the distance between 2 points P with coordinates x1, y1 and Q with coordinates x2, y2. The distance PQ equals the square root of x2 minus x1 squared plus y2 minus y1 squared. This comes directly from the Pythagorean theorem. For example, the distance between 6, -4, and 3, 0 is the square root of 9 plus 16, which equals 5 units. The section formula finds a point dividing a line segment in a given ratio. If a point divides the segment joining x1, y1 and x2, y2 in ratio mn, its coordinates are mx2 plus nx1 over m plus n for x, and similarly for y. The midpoint formula is simpler. When m equals n, the midpoint is x1 plus x2 over 2, y1 plus y2 over 2. The area of a triangle with vertices x1, y1, x2, y2, and x3, y3 equals 1/2 times the absolute value of x1 times y2 minus y3 plus x2 times y3 minus y1 plus x3 times y1 minus y2. If the area equals 0, the 3 points are collinear. They all lie on the same straight line. The slope of a line measures its steepness and direction. If a line makes angle theta with the positive x-axis measured counterclockwise, then the slope m equals tan theta. The inclination theta ranges from 0 to 180 degrees. A horizontal line has slope 0. A vertical line has undefined slope because tan 90 degrees is undefined. We can find slope from 2 points on a line. If a line passes through P of x1, y1 and Q x2, y2, then slope m equals y2 minus y1 divided by x2 minus x1. Note that x1 must not equal x2, otherwise the line is vertical. For example, the slope through 3, -2 and -1, 4 equals 6 divided by -4, which is -3/2. Two non-vertical lines are parallel if and only if their slopes are equal. This makes sense. Parallel lines have the same steepness and direction, so they must have the same angle of inclination. If m1 equals m2, the lines are parallel. Conversely, parallel lines have equal slopes. Two lines are perpendicular if the product of their slopes equals -1. That is, m1 times m2 equals -1. This means the slopes are negative reciprocals of each other. m2 equals -1 over m1. For example, lines with slopes 2 and -1/2 are perpendicular. The angle between two lines with slopes m1 and m2 can be found using tan theta equals the absolute value of m2 minus m1 divided by 1 plus m1 times m2. This gives the acute angle between the lines. When m1 times m2 equals -1, the denominator is 0, confirming perpendicular lines form a 90-degree angle. Horizontal and vertical lines have special equations. A horizontal line has equation y equals a constant, like y equals 3. Its slope is 0. A vertical line has equation x equals a constant, like x equals 5. Its slope is undefined. These are the simplest line equations. The point-slope form gives the equation of a line through a given point with a given slope. If a line passes through x1, y1 with slope m, its equation is y minus y1 equals m times x minus x1. This is the most basic form of a line equation. For example, a line through 2, 3 with slope 4 has equation y minus 3 equals 4 times x minus 2. The two-point form gives the equation when we know 2 points on the line. If a line passes through x1, y1 and x2, y2, the equation is y minus y1 over y2 minus y1 equals x minus x1 over x2 minus x1. This comes directly from the slope formula and point-slope form. The slope-intercept form is y equals mx plus c, where m is the slope and c is the y-intercept. The y-intercept is where the line crosses the y-axis at point 0c. For example, y equals 2x plus 3 has slope 2 and crosses the y-axis at 0, 3. This form is very useful for graphing lines. The intercept form is x over a plus y over b equals 1, where a is the x-intercept and b is the y-intercept. The line crosses the x-axis at a0 and the y-axis at 0b. For example, x over 3 plus y over 4 equals 1 represents a line crossing the axes at 3, 0 and 0, 4. The general form of a line equation is ax plus b plus c equals 0, where a, b, and c are real numbers, and a and b are not both 0. Every line equation can be written in this form. For example, 2x plus 3y minus 6 equals 0 represents a line. This form is useful for finding distances. The distance from a point x1, y1 to a line ax plus b plus c equals 0 is given by the absolute value of ax1 plus by1 plus c divided by the square root of a squared plus b squared. This is the perpendicular distance. For example, the distance from 2, 3 to the line 3x plus 4y minus 5 equals 0 is mod 6 plus 12 minus 5 over 5, which equals 13 over 5 or 2.6 units. The distance between two parallel lines ax plus b plus c1 equals 0 and ax plus b plus c2 equals 0 is c1 minus c2 divided by the square root of a squared plus b squared. Parallel lines have the same coefficients a and b, just different constants. The distance is constant throughout their length. Watch out for common mistakes. Don't reverse the order in the slope formula. It's y2 minus y1 over x2 minus x1. Remember the absolute value in distance formulas. Always convert to general form before using the distance formula. Be careful with signs in the intercept form. Key formulas to memorize. Slope m equals y2 minus y1 over x2 minus x1. Point-slope form, y minus y1 equals m times x minus x1. Slope-intercept form, y equals mx plus c. General form, ax plus b plus c equals 0. Distance from point to line, ax1 plus by1 plus c over the square root of a squared plus b squared. Problem-solving strategy. First, identify what information is given, points, slope, intercepts, or angle. Choose the appropriate form of the line equation based on what's given. Convert between forms as needed. Always verify your answer by checking that given points satisfy your equation. Let's find the equation of a line through 2, 3, and 4, 7. First, calculate the slope. M equals 7 minus 3 over 4 minus 2 equals 4 over 2 equals 2. Using point-slope form with point 2, 3, y minus 3 equals 2 times x minus 2. Simplifying, y equals 2x minus 1. Calculate the distance from point 2, 3 to the line 3x plus 4y minus 5 equals 0. Using the formula, distance equals going 3 times 2 plus 4 times 3 minus 5 divided by the square root of 9 plus 16. That's 6 plus 12 minus 5 over 5, which equals 13 over 5 or 2.6 units. This is the perpendicular distance. Straight lines have many real-life applications. GPS navigation systems use coordinate geometry to find routes. Computer graphics and video games rely heavily on line equations. Architects and engineers use these concepts in construction. In physics, the trajectory of objects under constant velocity follows a straight line path. In this chapter, we learned that slope defines a line's steepness and direction. We studied multiple forms of line equations: point-slope, two-point, slope-intercept, intercept, and general forms. Parallel lines have equal slopes, while perpendicular lines have slopes whose product is -1. We derived formulas for distance from a point to a line and between parallel lines. Thank you for joining Chapter 9 on straight lines. Welcome to Chapter 10, Conic Sections. These beautiful curves, circles, ellipses, parabolas, and hyperbolas are obtained when a plane intersects a double-napped cone. The Greek mathematician Apollonius named them around 200 BC. These curves have remarkable applications. Planetary orbits follow ellipses, satellite dishes use parabolas, and hyperbolas guide navigation systems. Imagine a double-napped cone, two cones joined at their vertices. The cone has a vertex at the tip, an axis running through its center, and generators, which are lines on its surface. When a plane cuts through this cone at different angles, we get different curves. The angle between the plane and the vertical axis determines which conic section we obtain. The four main conic sections depend on angle beta. When beta equals 90 degrees, the plane is perpendicular to the axis, giving a circle. When alpha is less than beta less than 90 degrees, we get an ellipse. When beta equals alpha, the plane is parallel to a generator, giving a parabola. When beta is less than alpha, the plane cuts both naps, producing a hyperbola. Degenerate conics occur when the plane passes through the vertex. When alpha is less than beta less than or equal to 90 degrees, we get just a point. When beta equals alpha, the plane contains a generator, giving a single line, a degenerate parabola. When beta is less than alpha, we get a pair of intersecting lines, a degenerate hyperbola. A circle is the simplest conic section. It's the set of all points in a plane that are equidistant from a fixed point, called the center. The constant distance from the center to any point on the circle is called the radius. Every point on a circle is exactly the same distance from the center. The equation of a circle with center hk and radius r is x minus h squared plus y minus k squared equals r squared. When the center is at the origin, this simplifies to x squared plus y squared equals r squared. For example, a circle with center 0, 0 and radius 5 has equation x squared plus y squared equals 25. The general form of a circle equation is x squared plus y squared plus 2gx plus 2fy plus c equals 0. From this form, the center is at negative g, negative f, and the radius is the square root of g squared plus f squared minus c. To convert to standard form, complete the squares for both x and y terms. A parabola is the set of all points equidistant from a fixed line called the directrix, and a fixed point called the focus. The focus must not lie on the directrix. The axis of the parabola is the line through the focus perpendicular to the directrix. The vertex is where the parabola intersects its axis. The standard equations of parabolas depend on orientation. Y squared equals 4ax opens to the right with focus at a0. Y squared equals negative 4ax opens to the left. X squared equals 4ay opens upward. X squared equals negative 4ay opens downward. The coefficient determines the direction, and the variable squared determines the axis of symmetry. The lattice rectum of a parabola is a line segment through the focus, perpendicular to the axis, with endpoints on the parabola. Its length equals 4a, where a is the distance from vertex to focus. For example, if a equals 2, the lattice rectum has length 8. This is the focal chord perpendicular to the axis. An ellipse is the set of all points where the sum of distances from two fixed points called foci is constant. This constant sum equals 2a, where a is the semi-major axis. The center is at the midpoint between the foci. Unlike a circle, an ellipse has two axes of different lengths. The standard equation of an ellipse with center at the origin is x squared over a squared plus y squared over b squared equals 1, where a is greater than b. The major axis has length 2a along the x-axis. The minor axis has length 2b along the y-axis. If b is greater than a, the major axis is vertical. Key ellipse properties. The foci are located at plus or minus c0, where c squared equals a squared minus b squared. The vertices are at plus or minus a0 and 0 plus or minus b. The eccentricity e equals c over a, and it's always between 0 and 1 for ellipses. The lattice rectum length is 2b squared over a. A hyperbola is the set of all points where the difference of distances from two fixed points called foci is constant. This constant difference equals 2a. A hyperbola has two separate branches opening away from each other. Unlike an ellipse, the hyperbola extends infinitely in both directions. The standard equation of a hyperbola with center at the origin is x squared over a squared minus y squared over b squared equals 1. The transverse axis has length 2a along the x-axis. This connects the vertices. The conjugate axis has length 2b along the y-axis. Note the minus sign. This distinguishes hyperbola from ellipse. Key hyperbola properties. The foci are at plus or minus c0, where c squared equals a squared plus b squared. Note the plus sign, unlike ellipse. The vertices are at plus or minus a0. The eccentricity e equals c over a, and it's always greater than 1 for hyperbolas. The lattice rectum length is 2b squared over a. Asymptotes are lines that a hyperbola approaches but never touches. For the hyperbola x squared over a squared minus y squared over b squared equals 1, the asymptotes are y equals plus or minus b over a times x. These lines pass through the center and form an X shape. They're very helpful for sketching hyperbolas accurately. Eccentricity distinguishes the conics. For a circle, e equals 0, it's perfectly round. For an ellipse, e is between 0 and 1, it's elongated but closed. For a parabola, e equals exactly 1, the boundary case. For a hyperbola, e is greater than 1, it opens outward. The eccentricity measures how much the conic deviates from being circular. Watch out for common mistakes. Don't confuse ellipse and hyperbola equations. Remember the minus sign for hyperbola. Check signs carefully in standard forms. Use the correct formula for eccentricity, c over a for both, but c squared equals a squared minus b squared for ellipse, and c squared equals a squared plus b squared for hyperbola. Remember that a is always associated with the transverse axis. Key formulas to memorize. Circle, x minus h squared plus y minus k squared equals r squared. Parabola, y squared equals 4ax. Ellipse, x squared over a squared plus y squared over b squared equals 1. Hyperbola, x squared over a squared minus y squared over b squared equals 1. Remember the relationships between a, b, and c for each conic. Problem-solving strategy. First, identify the conic from the equation. Look for squared terms and their signs. Find the center, vertices, and foci using the appropriate formulas. Determine the direction of the axes. Sketch the curve using key points. Always verify your answer by checking that points satisfy the equation. Let's analyze the circle x squared plus y squared plus 8x plus 10y minus 8 equals 0. Group terms, x squared plus 8x plus y squared plus 10y equals 8. Complete squares, x plus 4 squared minus 16 plus y plus 5 squared minus 25 equals 8. Simplifying, x plus 4 squared plus y plus 5 squared equals 49. So center is -4, -5, and radius is 7. Analyze the parabola y squared equals 8x. Compare with the standard form y squared equals 4ax. We have 4a equals 8, so a equals 2. The focus is at a0, which is 2, 0. The directrix is x equals -a, which is x equals -2. The lattice rectum has length 4a equals 8. The parabola opens to the right. Conic sections have amazing real-life applications. Satellite dishes are parabolic to focus signals at the receiver. Planets orbit the sun in ellipses with the sun at one focus. Whispering galleries use elliptical shapes. A whisper at one focus can be heard clearly at the other. Cooling towers of power plants have hyperbolic shapes for structural strength. In this chapter, we learn that conics come from cone-plane intersections. A circle has all points equidistant from a center. A parabola has points equidistant from a focus and directrix. An ellipse has points where the sum of distances from two foci is constant. A hyperbola has points where the difference of distances from two foci is constant. Each has a standard equation and important properties. Thank you for joining Chapter 10 on Conic Sections. Welcome to Chapter 11, Introduction to Three-Dimensional Geometry. While we've studied points in a plane using two coordinates, real life often requires 3 dimensions. Think of a ball thrown in space, an aeroplane flying, or a ceiling fan. All need 3 coordinates to locate. The great mathematician Leonhard Euler helped develop these concepts. We'll extend our 2D knowledge to 3D space. In 3 dimensions, we have 3 coordinate axes. Imagine 3 planes intersecting at point O, all mutually perpendicular. The lines where they intersect are called the x-axis, x prime ox, y-axis, y prime oy, and z-axis, z prime oz. These 3 axes form what we call the rectangular coordinate system in 3 dimensions. They're all perpendicular to each other. The 3 coordinate planes are: the xy plane, horizontal, called XOY, the YZ plane, called YOZ, and the ZX plane, called ZOX. Think of the XY plane as the floor, and the other two as perpendicular walls. These three planes are mutually perpendicular to each other, just like the floor and two adjacent walls of a room. Just as two perpendicular lines divide a plane into 4 quadrants, 3 perpendicular planes divide space into 8 parts called octants. They're named XOYZ, X'(OYZ), X'(OY') and so on. We denote them by Roman numerals I through VAID. Each octant has a different combination of positive and negative coordinates. The sign convention follows naturally. Distances measured along OX, OY, and OZ are positive. Distances measured along OX', OY', and OZ' are negative. For example, in octant I, all coordinates are positive, plus, plus, plus. In octant 8, the signs are plus, minus, minus. The signs tell you which octant a point lies in. A point P in space has 3 coordinates, x, y, z. The x-coordinate is the perpendicular distance from the YZ plane. The y-coordinate is the perpendicular distance from the ZX plane. The z-coordinate is the perpendicular distance from the xy plane. Together, these 3 numbers uniquely determine the point's position in space. To find the coordinates of a point P, we use a step-by-step process. First, drop a perpendicular PM to the xy plane. Then, from point M, draw a perpendicular ML to the x-axis, meeting it at L. The distances are OL equals x, LM equals y, and MP equals z. So the coordinates of P are x, y, z. Special points have simple coordinates. The origin O is at 0, 0, 0. Any point on the x-axis has coordinates x, 0, 0. Only x is non-zero. Similarly, points on the y-axis are 0, y, 0, and points on the z-axis are 0, 0, z. 2 coordinates are always 0 for points on axes. Points on coordinate planes have one coordinate 0. A point in the xy plane has coordinates x, y, 0. The z-coordinate is 0 because it's on the xy plane. Similarly, points in the yz plane are 0, yz, and points in the zx plane are x, 0, z. One coordinate is always 0 for points on coordinate planes. Here's the complete sign pattern for all 8 octants. Octant 1 plus plus plus, octant 2 minus plus plus, octant 3 minus minus plus, octant 4 plus minus plus, octant 5 plus plus minus, octant 6 minus plus minus, octant 7 minus minus minus, octant 8 plus minus minus. Memorize this pattern. The distance between 2 points P with coordinates x1, y1, z1 and Q with coordinates x2, y2, z2 is given by PQ equals the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. This is the 3D extension of the 2D distance formula based on the 3D Pythagorean theorem. The distance from the origin to any point Q with coordinates x, y, z is the square root of x squared plus y squared plus z squared. This is a special case of the distance formula where one point is the origin. For example, the distance of point 3, 4, 5 from the origin is the square root of 9 plus 16 plus 25, which equals the square root of 50. 3 points P, Q, and R are collinear if they lie on the same straight line. We check this by verifying that PQ plus QR equals PR. This is the same condition we used in 2D geometry. Calculate all 3 distances using the distance formula, and if the sum of 2 equals the third, the points are collinear. The section formula in 3D finds a point dividing a line segment in a given ratio. If point R divides PQ in ratio n, then R's coordinates are mx2 plus nx1 over m plus n, my2 plus ny1 over m plus n, mz2 plus nz1 over m plus n. This extends naturally from the 2D section formula by adding the z-coordinate. The midpoint formula is a special case of the section formula when m equals n. The midpoint m of segment joining p of x1, y1, z1 and q of x2, y2, z2 is x1 plus x2 over 2, y1 plus y2 over 2, z1 plus z2 over 2. Simply take the average of corresponding coordinates. This divides the segment in ratio 1:1. Three-dimensional geometry has many real-life applications. GPS navigation systems use 3D coordinates to locate positions on Earth. Computer graphics and 3D modeling rely heavily on these concepts. Architects and engineers use 3D geometry in construction. In physics, we describe motion through space using 3 coordinates. To verify if 3 points form a right triangle, use the distance formula to find all 3 sides. Then check if the Pythagorean theorem holds. The sum of squares of 2 sides should equal the square of the third side. If this is true for any pair of sides, the triangle is right-angled at the third vertex. To verify if 4 points form a parallelogram, check that opposite sides are equal in length. Use the distance formula to calculate all 4 sides. If AB equals CD and BC equals DA, then ABCD is a parallelogram. Note that the diagonals may not be equal. If they are, it's also a rectangle. Watch out for common mistakes. Don't mix up the order of coordinates. It's always X, Y, Z. Be careful with signs when determining octants. Remember that points on coordinate planes have one coordinate 0, not 2. When applying the distance formula, make sure you're subtracting corresponding coordinates correctly. Key formulas to memorize. Distance between 2 points, square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Distance from origin, square root of x squared plus y squared plus z squared. Section formula, weighted average of coordinates. Midpoint, average of corresponding coordinates. Problem-solving strategy. First, identify the coordinates of all points involved. Apply the appropriate formula based on what you need to find, distance, midpoint, or section point. For geometric verifications, check the relevant conditions, collinearity, right angle, or equal sides. When possible, visualize the situation in 3D space. Let's find the distance between P of 1, -3, 4, and Q, -4, 1, 2. Using the formula, PQ equals the square root of -4 minus 1 squared plus 1 minus -3 squared plus 2 minus 4 squared. That's the square root of -5 squared plus 4 squared plus -2 squared, which equals the square root of 25 plus 16 plus 4, giving the square root of 45, or 3 times the square root of 5. Check if points P of -2, 3, 5, Q, 1, 2, 3, and R, 7, 0, -1 are collinear. Calculate. PQ equals the square root of 14. QR equals 2 times the square root of 14. PR equals 3 times the square root of 14. Since PQ plus QR equals the square root of 14 plus 2 times the square root of 14 equals 3 times the square root of 14, which equals PR, the points are collinear. Find the octant for point -3, 1, 2. The x-coordinate is negative, y is positive, and z is positive. Looking at the sign table, negative plus plus corresponds to octant 2. For point -3, 1, -2, the signs are negative plus negative, which corresponds to octant cis. The signs determine the octant. In this chapter, we learned that the 3D coordinate system has 3 axes and 3 planes. A point is located by 3 coordinates, x, y, z. The 8 octants are determined by the signs of the coordinates. The distance formula extends naturally from 2D to 3D by adding the z component. The section and midpoint formulas also extend by including the z-coordinate. Thank you for joining Chapter 11 on Introduction to Three-Dimensional Geometry. Welcome to Chapter 12, Limits and Derivatives. This is your introduction to calculus, one of the most powerful branches of mathematics. Calculus studies how function values change as inputs change. Sir Isaac Newton, working in the 17th century, was one of the founders of calculus. As the mathematician Whitehead said, with calculus as a key, mathematics can successfully explain the course of nature. Let's develop an intuitive understanding of derivatives. Imagine a body dropped from a tall cliff. Physics tells us the distance fallen equals 4.9 times t squared meters, where t is time in seconds. We want to find the velocity at exactly t equals 2 seconds. How do we find velocity at a single instant? We use average velocities over smaller and smaller time intervals. Average velocity equals distance traveled divided by time interval. Between t equals 0 and t equals 2 seconds, the body falls 19.6 meters, giving average velocity 9.8 meters per second. Between t equals 1 and t equals 2, it falls 14.7 meters in 1 second, giving 14.7 meters per second. As we make intervals smaller, the average velocity approaches about 19.6 meters per second. The instantaneous velocity at t equals 2 is the limit of average velocities as the time interval approaches 0. This is the derivative of the distance function at t equals 2. Geometrically, it equals the slope of the tangent to the distance-time curve at that point. The derivative captures the instantaneous rate of change. The limiting process is fundamental to calculus. We take smaller and smaller intervals around the point of interest. The average rate of change approaches a definite value, the limit. This limit gives us the instantaneous rate of change, or derivative. This idea revolutionized mathematics and physics. What exactly is a limit? We write limit as x approaches a of f of x equals L. This means as x gets closer and closer to a, the values of f of x get closer and closer to L. The limit represents the value f of x should take at x equals a, based on its behavior near a. The function may or may not actually be defined at x equals a. The left-hand limit considers x approaching a from values less than a. We write limit as x approaches a minus of f of x. This is dictated by the values of f of x when x is to the left of a. Think of approaching a from the negative side on the number line. The right-hand limit considers x approaching a from values greater than a. We write limit as x approaches a plus of f of x. This is dictated by the values of f of x when x is to the right of a. Think of approaching a from the positive side on the number line. A limit exists only when the left-hand limit equals the right-hand limit. When both approach the same value L, we say limit as x approaches a of f of x equals L. If they differ, the limit does not exist. The function doesn't need to be defined at x equals a for the limit to exist. Let's find the limit of f of x equals x plus 10 as x approaches 5. For x near 5, like 4.9, 4.95, 4.99, the function values are 14.9, 14.95, 14.99. From the right, values are 15.01, 15.1. Both sides approach 15. So limit as x approaches 5 of x plus 10 equals 15. The algebra of limits makes calculations easier. The limit of a sum equals the sum of limits. The limit of a difference equals the difference of limits. The limit of a product equals the product of limits. The limit of a quotient equals the quotient of limits, provided the denominator's limit is not 0. Standard limits you should know. Limit as x approaches a of x equals a. Limit as x approaches a of x to the n equals a to the n. Limit as x approaches a of a constant equals that constant. And importantly, limit as x approaches 0 of sine x over x equals 1. This is crucial for trigonometric limits. For polynomials, finding limits is straightforward. Limit as x approaches a of p of x simply equals p of a. Just substitute x equals a into the polynomial. For example, limit as x approaches 2 of x squared plus 3x plus 1 equals 4 plus 6 plus 1, which equals 11. Direct substitution works perfectly. For rational functions, if the denominator is not 0 at x equals a, just substitute directly. If the denominator equals 0, factorize both numerator and denominator, cancel common factors, then evaluate. For example, limit as x approaches 2 of x squared minus 4 over x minus 2. Factor as x plus 2 times x minus 2 over x minus 2, cancel to get x plus 2, giving limit 4. Important trigonometric limits. Limit as x approaches 0 of sine x over x equals 1. Limit as x approaches 0 of 1 minus cos x over x equals 0. Limit as x approaches 0 of tan x over x equals 1. These standard results are used frequently in limit problems involving trigonometric functions. The derivative of a function measures its instantaneous rate of change. We define f prime of x as limit as h approaches 0 of f of x plus h minus f of x, all divided by h. This gives the slope of the tangent to the curve y equals f of x at any point. Other notations include dy over dx or d over dx of f of x. Finding a derivative from first principles means using the definition directly. Calculate f of x plus h minus f of x, divide by h, simplify, then take the limit as h approaches 0. For example, the derivative of x squared, the difference quotient, simplifies to 2x plus h, and as h approaches 0, we get 2x. The algebra of derivatives includes important rules. The derivative of a sum or difference equals the sum or difference of derivatives. The product rule, derivative of f times g equals f prime times g plus f times g prime. The quotient rule, derivative of f over g equals f prime times g minus f times g prime, all over g squared. A constant multiple comes out front. Standard derivatives to memorize. The derivative of x to the n equals n times x to the n minus 1. The derivative of sin x equals cos x. The derivative of cos x equals negative sin x. The derivative of any constant equals 0. These formulas save you from using first principles every time. Key formulas summary. Limit as x approaches a of f of x equals L when left and right limits coincide. Derivative, f prime of x equals limit as h approaches 0 of f of x plus h minus f of x over h. Product rule, f times g prime equals f prime g plus f g prime. Power rule, derivative of x to the n equals nx to the n minus 1. Problem-solving strategy. For limits, first check if left and right limits are equal. For derivatives, use the definition for simple functions or apply standard formulas and rules for complex ones. Always simplify expressions before taking limits. Factorize, cancel, and use algebraic manipulation to your advantage. Let's evaluate limit as x approaches 3 of x squared minus 9 over x minus 3. Factor the numerator as x minus 3 times x plus 3. Cancel x minus 3 from numerator and denominator. We get limit as x approaches 3 of x plus 3, which equals 6. Always simplify before evaluating. Find the derivative of f of x equals x cubed. Using the power rule, f prime of x equals 3x squared. From first principles, limit as h approaches 0 of x plus h cubed minus x cubed, all over h. Expanding and simplifying gives limit of 3x squared plus 3xh plus h squared over h, which equals 3x squared as h approaches 0. Derivatives have countless applications. In physics, velocity is the derivative of position and acceleration is the derivative of velocity. In economics, derivatives measure marginal cost and marginal revenue. Optimization problems use derivatives to find maximum and minimum values. Curve sketching relies on derivatives to understand function behavior. In this chapter, we learned that limits describe function behavior as x approaches a value. Left and right limits must be equal for the limit to exist. Derivatives measure instantaneous rate of change, the slope of the tangent line. Standard formulas for limits and derivatives simplify calculations. Calculus is fundamental to all of mathematics and science. Thank you for joining Chapter 12 on limits and derivatives. Welcome to Chapter 13, Statistics. Statistics is the science of collecting, analyzing, and interpreting data. Carl Pearson, a pioneer of statistics, lived from 1857 to 1936. You've already learned about measures of central tendency, mean, median, and mode, but these alone don't tell the whole story. We also need to understand how data is scattered or dispersed. Why study dispersion? Consider two batsmen with identical means of 53 runs. Batsman A scores range from 0 to 117, very inconsistent. Batsman B scores range from 46 to 60, very consistent. Same average, but completely different performance patterns. Central tendency alone can be misleading. We need to measure variability. The four main measures of dispersion are range, the simplest measure, quartile deviation, based on quartiles, mean deviation, using average of absolute deviations, and standard deviation, the most widely used measure. Each describes how scattered the data is around the central value. Range is the simplest measure of dispersion. It equals the maximum value minus the minimum value. For batsman A, range equals 117 minus 0 equals 117. For batsman B, range equals 60 minus 46 equals 14. The larger range indicates more scatter. It's quick and easy, but has limitations. Range has serious limitations. It only considers the two extreme values, ignoring all observations in between. It doesn't measure dispersion from any central tendency. A single outlier can dramatically change the range. We need more robust measures that use all the data. Mean deviation is the average of absolute deviations from a central value. It uses all observations, not just extremes. It measures scatter around the mean or median. The formula is MD of A equals sum of absolute values of xi minus A divided by n. This gives a single number representing average distance from center. Why use absolute values? Deviations from the mean can be positive or negative. In fact, the sum of all deviations from the mean equals 0. This is a mathematical property. If we didn't use absolute values, the mean deviation would always be 0. The absolute value represents the actual distance from the central value. Mean deviation about the mean is calculated as MD of x bar equals 1 over n times the sum of absolute values of xi minus x bar. First, calculate the mean x bar. Then find each deviation from the mean. Take absolute values of all deviations. Finally, average these absolute deviations. Mean deviation about the median uses the same process, but centers on the median m. MD of m equals 1 over n times sum of absolute values of xi minus m. First, find the median by arranging data in order. Calculate deviations from the median. Take absolute values and average them. Let's work through an example. Data 6, 7, 10, 12, 13, 4, 8, 12. Mean equals 72 divided by 8 equals 9. Deviations from mean, -3, -2, 1, 3, 4, -5, -1, 3. Absolute values, 3, 2, 1, 3, 4, 5, 1, 3. Mean deviation equals 22 divided by 8 equals 2.75. Variance is another measure of dispersion. It's the mean of squared deviations from the mean. The formula is sigma squared equals 1 over n times sum of xi minus x bar squared. Instead of absolute values, we square the deviations. This avoids the zero-sum problem and has nice mathematical properties. Standard deviation is the square root of variance. We write sigma equals square root of 1 over n times sum of xi minus x bar squared. Taking the square root brings the measure back to the original units. If data is in meters, variance is in meters squared, but standard deviation is in meters. This is the most widely used measure of dispersion. To calculate standard deviation, first find the mean of the data, then find each deviation from the mean. Square each deviation. Find the average of these squared deviations. That's the variance. Finally, take the square root to get standard deviation. A shortcut formula for variance avoids calculating individual deviations. Sigma squared equals 1 over n times sum of xi squared minus x bar squared. Alternatively, sigma squared equals 1 over n squared times sum of xi squared minus sum of xi squared. This is computationally more efficient, especially for large datasets. For group data with frequencies, standard deviation uses weighted calculations. Sigma squared equals 1 over n times sum of fi times xi minus x bar squared. Here xi is the class mark, phi is the frequency, and n is the total frequency. The principle is the same, but each value is weighted by its frequency. The coefficient of variation is a relative measure of dispersion. CV equals sigma over x bar times 100, giving a percentage. It's unit-free, allowing comparison between datasets with different units or scales. Higher coefficient of variation means more variability relative to the mean. Use coefficient of variation to compare different datasets. Suppose Team A has mean 100, standard deviation 10, giving CV of 10%. Team B has mean 50, standard deviation 8, giving CV of 16%. Team B is more variable relative to its mean, despite having a smaller absolute standard deviation. Standard deviation has important properties. It's independent of origin. Adding a constant to all values doesn't change the standard deviation. It scales with the data. Multiplying all values by a constant multiplies the standard deviation by that constant. Standard deviation of a plus bx equals absolute value of b times standard deviation of x. Watch out for common mistakes. Don't forget to take the square root when finding standard deviation from variance. Use the correct formula for grouped data with frequencies. Remember to use absolute values in mean deviation. Never compare standard deviations without considering the means. Use coefficient of variation instead. Key formulas to memorize. Range equals maximum minus minimum. Mean deviation equals 1 over n times sum of absolute values of xi minus a. Variance sigma squared equals 1 over n times sum of xi minus x bar squared. Standard deviation sigma equals square root of variance. Coefficient of variation equals sigma over x bar times 100. Problem-solving strategy. First, identify whether data is ungrouped or grouped. Choose the appropriate measure based on the question. Use shortcut formulas when they make calculations easier. When comparing variability between datasets, always use coefficient of variation for a fair comparison. Let's find the standard deviation of 2, 4, 6, 8, 10. Mean equals 30 divided by 5 equals 6. Deviations, -4, -2, 0, 2, 4. Squared deviations, 16, 4, 0, 4, 16. Variance equals 40 divided by 5 equals 8. Standard deviation equals square root of 8, approximately 2.83. Comparing our batsmen. Batsman A has mean 53, standard deviation 35.2, coefficient of variation 66.4%. Batsman B has mean 53, standard deviation 4.3, coefficient of variation 8.1%. Same means, but vastly different variability. Batsman A is much more inconsistent. The high coefficient of variation reveals this. Statistics has countless real-life applications. Quality control uses standard deviation to monitor manufacturing consistency. Finance uses it to measure investment risk. Sports analysts use it to evaluate player consistency. Scientists use it to analyze experimental data and determine significance. In this chapter, we learned that dispersion measures how spread out data is. Range is simplest but only uses extreme values. Mean deviation uses absolute values of deviations from a central value. Standard deviation is the most widely used measure, based on squared deviations. Coefficient of variation enables comparison between data sets with different scales. Thank you for joining Chapter 13 on Statistics. Welcome to Chapter 14, Probability. Probability is the mathematical study of chance and uncertainty. It quantifies how likely events are to occur. As John Arbuthnot said, where mathematical reasoning can be had, it's folly to use any other. Probability forms the foundation for statistics and helps us make informed decisions under uncertainty. A random experiment has uncertain outcomes. We know all possible outcomes in advance, but cannot predict which specific outcome will occur. Examples include tossing a coin, rolling a die, or drawing a card from a deck. Each trial of the experiment produces one outcome from the set of all possibilities. The sample space is the set of all possible outcomes of an experiment. We denote it by S. For a single coin toss, S equals head-tail. For two coins, S equals HHHTTHTT. For rolling a die, S equals 1, 3, 4, 5, 6. The sample space serves as the universal set for all probability questions about that experiment. An event is any subset of the sample space. If we toss two coins and want exactly one head, the outcomes HT and TH form the event E equals HTTH. Events correspond to subsets of S. The event occurs if the actual outcome is in the event set. This connection between events and sets is fundamental. Types of events. An impossible event is the empty set. It can never occur. A sure event is the entire sample space S. It always occurs. A simple event has just one outcome, like getting a 6 on a die. A compound event has multiple outcomes, like getting an even number, which includes 2, 4, and 6. Two events are mutually exclusive if they cannot occur together. Their intersection is empty, no common outcomes. For example, getting an odd number and getting an even number on a single die roll are mutually exclusive. A number cannot be both odd and even simultaneously. Mutually exclusive events have no overlap. Events are exhaustive if together they cover the entire sample space. The union of all events equals S. At least one of them must occur when the experiment is performed. For a die, the events odd number and even number are exhaustive. Every outcome is either odd or even. Together, they cover all possibilities. Complementary events are pairs like A and not A, written as A prime. A prime equals S minus A. Event A and its complement A prime are mutually exclusive. They have no overlap. They're also exhaustive. Together, they cover everything. For a die, if A is even number, then A prime is odd number. The algebra of events uses set operations. A or B means A union B, outcomes in either event. A and B means A intersection B, outcomes in both events. A but not B means A minus B, outcomes in A but not in B. Not A means A prime or S minus A. These operations combine events meaningfully. Let's combine events for a die roll with sample space 1 through 6. Let A be prime number equals 2, 3, 5. Let B be odd number equals 1, 3, 5. A or B equals 1, 2, 3, 5, all prime or odd numbers. A and B equals 3, 5, numbers that are both prime and odd. A but not B equals 2 prime but not odd. The axiomatic approach to probability defines 3 rules. First, probability of any event E is greater than or equal to 0. Second, probability of the sure event S equals 1. Third, for mutually exclusive events A and B, probability of A or B equals probability of A plus probability of B. From these, we can derive probability of the impossible event equals 0. Each outcome omega I in the sample space has a probability p of omega I. Each individual probability is between 0 and 1. The sum of all individual probabilities equals 1. For any event A, its probability equals the sum of probabilities of all outcomes in A. This connects individual outcome probabilities to event probabilities. When all outcomes are equally likely, each has probability 1 over n, where n is the total number of outcomes. Then probability of event A equals the number of outcomes in A divided by n. We write P of A equals size of A divided by size of S. This is the classical definition of probability for equally likely outcomes. To calculate probability, count the favorable outcomes, those in your event. Count the total outcomes, the size of sample space. Divide favorable by total. For example, probability of rolling an even number on a die. Favorable outcomes are 2, 4, 6, so 3 favorable. Total is 6. Probability equals 3 over 6, which equals 1/2. Example with 2 coins. Sample space is HHTTHTT, 4 outcomes. Event exactly 1 head is HTTH, 2 outcomes. Probability equals 2 over 4 equals 1/2. Event at least 1 head is HHTTH, 3 outcomes. Probability equals 3 over 4. Count outcomes carefully for accurate probabilities. The addition rule. P of A union B equals P of A plus P of B minus P of A intersection B. For mutually exclusive events where A intersection B is empty, this simplifies to P of A union B equals P of A plus P of B. The subtraction accounts for double counting outcomes in both events. This general formula works for any events. The complement rule states P of A prime equals 1 minus P of A. The probability of not A equals 1 minus probability of A. This is useful when A prime is easier to calculate than A. For example, probability of not rolling a 6 on a die equals 1 minus 1/6 equals 5/6. Sometimes it's easier to count what you don't want. Probability always lies between 0 and 1 inclusive. P of A equals 0 means an impossible event. It can never occur. P of A equals 1 means a sure event. It always occurs. Any probability outside this range indicates an error in calculation. Probabilities can be expressed as fractions, decimals, or percentages. Watch out for common mistakes. Don't add probabilities without checking if events are mutually exclusive. Remember to subtract the intersection in the addition rule. Always verify events are mutually exclusive before using the simplified addition formula. If your probability exceeds 1 or is negative, you've made an error. Key formulas to memorize. P of A equals favorable outcomes divided by total outcomes for equally likely cases. Addition rule. P of A union B equals P of A plus P of B minus P of A intersection B. Complement rule. P of A prime equals 1 minus P of A. For mutually exclusive events, P of A union B equals P of A plus P of B. Problem-solving strategy. First, define the sample space clearly. List all possible outcomes. Identify the events of interest as subsets of the sample space. Check whether events are mutually exclusive or have overlap. Apply the appropriate probability rules, addition rule, complement rule, or direct counting. Find probability of prime or even on a die. A equals prime equals 2, 3, 5. B equals even equals 2, 4, 6. A union B equals 2, 3, 4, 5, 6. That's 5 outcomes. Probability equals 5 over 6. Alternatively, using addition rule, P of A equals 3 over 6, P of B equals 3 over 6, P of A intersection B equals 1 over 6. So P equals 3 over 6 plus 3 over 6 minus 1 over 6 equals 5 over 6. 2 dice example. There are 36 equally likely outcomes. To find probability that sum equals 7, count the favorable pairs. 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. That's 6 outcomes. Probability equals 6 over 36 equals 1/6. Sum of 7 is the most likely outcome when rolling 2 dice. Understanding the sample space is crucial. Probability has countless real-life applications. Weather forecasts use probability to predict rain chances. Insurance companies use probability to assess risk and set premiums. Quality control uses probability to determine acceptable defect rates. Games and gambling are built on probability calculations. Understanding probability helps make better decisions. In this chapter, we learn that probability quantifies uncertainty. The sample space contains all possible outcomes. Events are subsets of the sample space. For equally likely outcomes, P of A equals favorable divided by total. The addition and complement rules simplify calculations. Thank you for joining Chapter 14 on probability, and congratulations on completing the Class 11 Mathematics video series.